Today I'm presenting on research done at the Portland University of Science and Technology with the International Research Experience for Students BioFlow program. This was a NSF-funded program sponsored by Cleveland State University. Again, I'd like to thank both of my mentors, Jiwon Kim and Yundo Kim, as well as advisors, Dr. Lee from Postec and Dr. Zhang from Cleveland State. So to begin, particulate matter, or PM matter, is one of the main global environmental issues right now. As well, PM matter, when we got into the body, can cause different health concerns, such as cardiovascular, respiratory, as well as some carcinogenic diseases. Then, PM particles, when suspended in aqueous solutions, they can also cause many issues, including the developmental issues of organisms, as well as growth innovation for plant life. Currently, the methods to measure PM particles have many limitations. These include that the large sampling stations, they're very large, they're cumbersome, we need specialized people to use them, as well as very, very expensive. And the handheld devices, they have low measurement accuracy for high concentrations, and they are still quite expensive. You'll be paying up to $3,500 just to have an error rate that's within 10%. Additionally, because they use light scattering techniques, they are not accurate when we're looking at high concentration of PM matter. So the goal of our research is to create a real-time measurement of high PM concentration with deep learning, the handheld smartphone-based device with a goal of around $400. This device should be able to measure both homogeneous solutions as well as heterogeneous solutions of varying PM particles. Quick overview of our process. First, we acquire some raw data, pass that through some digital image processing that provides us with a trainable data set we can put into our model, and that trains and optimizes our model called HoloSpeckleNet. HoloSpeckleNet is then applied to various samples to produce concentration predictions of that PM matter. For our method, the way that we're actually visualizing things is with a technique called digital holographic microscopy, or DHM. DHM is a frequently used method for measuring three-dimensional position and size of particles in a 3D space. However, there are some limitations with DHM. DHM requires expensive precision optical equipment, as well as it normally has a high computational cost. However, the advances of both smartphone as well as with some deep learning techniques in the past years can solve many of these issues. That expensive optical setup can be replaced with smartphones, so getting cheaper and stronger every single year, as well as some of that computation can be traded off for computation in a deep learning or an AI-generated device. And here are just some of the many papers recently that are showcasing these advances. So for our project, we have a smartphone-based device, as shown in this image right here, where we have samples suspended in water that are hit with a laser to produce the digital holographic microscopy images. These samples are a mix of fine and coarse PM particles. Fine particles are those that are with a diameter of about less than 2.5 micrometers, often called PM 2.5, and coarse PM are particles with a diameter between 5 and 10 micrometers, commonly PM 10. On the right, we can see the distribution of our samples. We have black, pure fine, red, homogeneous, coarse, and the mixture of red and black make up our blue samples, the heterogeneous mixtures. And our goal is to create two different models, one for fine, one for coarse, and use those models to predict how much of red and black make up the blue right there. So for the holographic images, if you have an instance where you have low concentration, you're going to get these really clear circular patterns from each particle. It's just really, really obvious where the particles are. However, when you increase the concentration in a sample in the laser space, all those different speckle patterns are going to interfere on one another, creating this really noisy, wavy speckle pattern that's hard to decipher exactly what's in there. And that's where the deep learning methods really come into play. By taking tons of different speckle patterns and assigning class numbers to them, we can train a model to detect those changes that we can visually tell, but we might not be able to quantify ourselves. The model can do that for us and then predict what concentration of particulate matter is in that sample. The process we have, we take our raw videos, these are slow-mo videos from the cell phone, we parse them into consecutive frames, then each frame undergoes an RGB to grayscale conversion, as well as an ensemble averaging to remove the background noise. From that point, we take these raw frames, go through both a high-pass or a low-pass filter, as well as running a few different image processing, including an intensity intensity shifting, contrast enhancement, and image segmentation to a smaller size. For this process, the three hyperparameters we can control are filter size, the contrast enhancement value, and the intensity shifting value. So for our raw signals, we need to separate them from the heterogeneous mix of fine and coarse PM into homogeneous signals of just those two elements. The way we did that was a 2D Gaussian spatial filter, where any image that's passed through a high-pass filter can retain just the signal of the fine PM particles, while images passed through a low-pass filter will contain the signal of coarse PM particles. Then those two images, the high-pass and low-pass filtered images, can be passed into our model to produce a prediction. Our deep autoencoder network is comprised of multiple restricted Boltzmann machine layers, where each layer can extract a representative feature of said image that's passed in. And the latent space contains 64 features that are then passed into a regression model to produce an actual prediction of said concentration. And this can pick up on those nuanced differences in those images that I was talking about earlier, and then give us our final result. Here are just some examples of the raw, high-pass, and low-pass images for both fine, coarse, and in mixture. Once again, you can visually tell there are differences in these images for each of those cases, and that's a specific thing that our model is picking up on as it learns how to train and produce these results. Speaking of results, our first one is for the fine PM particles. Up in the top left, we have homogeneous PM10 or PM2.5 solution. This passed a high-pass filter, and then we go through and we train and optimize the three parameters I mentioned, which then produces the hollow speckle net for fine PM. This is then applied on a heterogeneous mixture of both fine and coarse particles. High-pass filter passed through our model, and we produce a prediction. The left figure is for the homogeneous case, where we have the ground truth versus predicted value. Ideally should be a one-to-one relation between the two. You can see it's pretty good. Then we have a heterogeneous mixture, again, ground truth versus predicted PM concentrations. And the key thing we're looking at that figure is the difference of including or excluding the high-pass filter. Where blue is using the high-pass filter, gray is without, just doing the model on the pure raw data. And you can both visually and with the root mean squared error bars pretty clearly tell that the high-pass filter does in fact work. It makes a quantifiable difference in the accuracy of our predictions. This was definitely a good point that validated our results in our method as we were working through this. Then on to coarse particles. Again, homogeneous coarse, run through, optimize parameters, get thing, apply in heterogeneous. Oh no, it didn't work. We had some issues where we couldn't get the coarse PM with the same method. The reason this actually ended up happening is when you apply the low-pass filter, you're not fully removing the signal from the fine particles. So what we had to do is we had to run the same model on the fine particles, get their low-pass filter noise, and effectively create a linear correction factor to offset the prediction of just the coarse and the heterogeneous. So once again, here's the homogeneous solution of ground versus predicted. But the key thing looking at is the heterogeneous guy. Here, instead of looking at using the low pass or not using the low pass, the key thing we're looking at is the blue, red, black is all with the correction factor. The gray values is what happens if we don't include that correction factor from applying the low pass filter on that homogeneous fine particles. And you can see that all the gray data, it does look roughly linearly shifted above the ideal one-to-one line. So this is showing that the correction factor from the low-pass filter on the fine particles does in fact bring our data back down to what we would expect on that one-to-one line. So in conclusion, we were able to create a smartphone-based digital holographic microscopy device. It was about $390. That is able to detect the concentration of both fine and coarse particles from either homogeneous or heterogeneous mixtures using deep learning training. This is a cost-effective device that is easy to implement anywhere you want, and this study can be used to develop cost-effective devices for monitoring microparticles suspended in various media. Thank you for your time.